Hi, welcome to the 7th Milan Video Tech meetup. Today, we're going to speak about WebAssembly, digital rights management in video, video monitoring, and error KPIs in IPTV and OTT. We are part of the 24 hours mega meetup, so thanks, and thanks also to the organizers, and hope you enjoy today's session. So, let's pick up where we left off last time. At the last meetup, we had an I can tell on what's video today in 2021. We covered topics like live, data quality, interactive volumetric video, and smart encoding. For today's session, we're going to be the speaker, Behnam from Evolution, myself, Alexey Malikov from Elecard, and Luca Moglia from Akamai. What's the agenda for today? We're going to talk about See the Future, or WebAssembly as means for web playback by Behnam. Then we're going to look at how does a video DRM system work. Then we're going to look at video monitoring dashboards with near real-time edge logs and CMCD KPIs by Luca. And last but not least, we're going to talk about metrics and key indicators of faults and malfunctions in OTT IPTV media content delivery by Alexey.
Hi everyone, hope you are enjoying these wonderful talks at the 24-hour mega meetup. And my name is Behnam, and I've been doing video streaming stuff, VOD and live since 2010. And currently I am the video R&D lead engineer at the Evolution. Evolution is the leading and biggest provider, B2B provider of live casino since 2006. We have offices and studios in 20 countries, and with more than 800 tables. Each table is a live streaming studio, and we are serving these live streams globally 24/7. And as it is very clear, the live streaming sits at the heart of our business, and in order to generate and deliver these live streams, we developed our own video platform. We are serving and playing our videos on the browsers, and on the Androids and desktops, we are delivering these videos over WebSocket, and with the glass-to-glass latency between 1.5 to 3 seconds, and using media source extension for playback. And on the iPhones, on the other hand, we are using the HLS. The latency over the HLS is between 3.5 seconds with very small gap sizes up to 7 seconds. And given the nature of our games, which involves the interaction between the game presenters and the players, that means that the latency is important for us. What is WebAssembly? And I'm sure most of you are already aware of it. Just a quick recap. AKA WASM. It's a cross-platform binary standard to run pre-compiled code on any web browser, on any device, on any platform. And compiled code means optimized code, more optimization, faster. And typically the performance of the WebAssembly compared to interpreted JavaScript is 3 to 4 times better. But of course that depends on your code and the application. And you will have the freedom of choosing freedom of choice between multiple backend languages like C, C++, Rust, Go, and WebAssembly helps you generate a binary that is runnable on all browsers, and that instantly means that you will have access to a big library, a number of free and open source libraries, and use them to add features to your web applications. And why did we choose the WASP technology to develop our player? First of all, we want to achieve consistency across all platforms and on all devices, not using the HLS on the iPhones. With higher latency, having the same latency everywhere will be a big help for us. Also, we are having the target to achieve sub-second latencies. And for that, it would be very good to have direct access to the decode function, something that the browsers right now don't provide that. We are hoping that in futures the web codecs give everybody that. And having access to the decode function and everything, all the full chain of the video playback will have its own perks. We would love to gain access to the and being able to manage the playback buffer, in terms of deciding what to do when the packet drops or frame drops are happening, or choosing the lowest latency possible from receiving the frame up to playing it back, or reliability. That will be our choice. The codec support currently, the most widely supported codec is H.264. It's everywhere almost, and other codecs like the AV1 and VP9 are not supported everywhere else. We would love to have support of the newer generation codecs on everywhere, actually. That is a must for us with our newer games coming out, like in less than a month. In future, we are going to have this live VR games that is going to use higher than HD resolutions, and the H.264 does not seem to be the best choice in that case. So with the WebAssembly, we can deliver add the support of such codecs faster. We would be able to actually support any transport protocol that we want, apart from those ones that are supported in the browsers, like the WebSocket, like the Quick. We may be able even to do something completely customized and in-house. You might ask, why didn't we choose the Apple low latency HLS, for example? Well, the thing is that with the Apple low latency HLS, it's good for the latency around 2 seconds, and it won't be that much better than what we are doing right now. Our target is below 1 second, and as soon as we are talking about sub-second latency, Webrtc seems like a very obvious choice. But again, there are some limitations with the Webrtc. For example, codec limitations. You have to use the H.264 in baseline profile. For example, if you want to go with the AVC, then on the Webrtc, then that means that you are going to pay high price in terms of the quality and bandwidth. We've done testing and seen that in order to achieve the same quality as of today that we are delivering with the baseline profile, we have to add up to our bandwidth significantly, and that means added costs of delivery, and that is not something that we are looking forward to. So just a quick comparison between what will you get if you are using built-in features of the browsers. You may use the HTML5 video tag. It takes a source URL and controls the full pipeline. No hassle, no headache. But you will have, on the other hand, limited control over different parts of the playback. And the implementation may differ across different browsers, something that you may have to consider while developing your application. Another choice would be the media source extension. It ingests input source and controls almost all video playback aspects. Again, it's not available on the iPhones, and in both cases there is no licensing cost. You don't have to think about it. The browser vendor most likely already paid for those that part, since the codec is delivered to you as part of the browsers. With the custom components, in this case it would be WASM and WebGL, for example. What you get would be any codec. You can deliver any codec. You can customize buffer management for low latency playback or reliability based on your choice. And you will have a wider choice of transport protocol. But on the other hand, there will be higher battery usage. Currently, we are achieving between 80 to 90% of the HLS native playback on mobile devices. And that is essentially because we are delivering a software decoder, and we're doing software decoding. There is no hardware acceleration. So it is normal to have higher battery usage. There will be size penalty. You will have to deliver a bigger binary that incorporates everything that's needed, decoders and all the helper code in there. And there may be licensing costs, especially with the MPEG codecs, HEVC, AVC, or VVC in future, or any VC. And in case of the AVC, it's pretty straightforward. You can contact the MPEG-LA, they will give you complete information, and there's a minimum number of deliveries of the codec, and there's a cap. It's pretty clear cut. But HEVC, you have to, I don't know, consult who. It's very complicated. You could go instead for VP9 and AV1, something which is not readily available in all browsers right now. In future, hopefully, the web codecs, when it's becoming the standard, you will be able to get that decode function. Then you don't have to worry about the codec and licensing part. But for now, it's not the case yet. Hopefully, it will be in future. And you can use the WebGL to do custom rendering and color space management. You can apply some fancy rendering. You will have the choice to do that. What is the workflow look like? Well, this is how we are doing it right now. We compile a C-based decoder libraries. We are choosing and using the libav and the FFmpeg libraries. Kudos to the FFmpeg guys, libav guys. Thank you very much. You've been doing great job, and basically you are supporting the whole video industry for a very long time right now. And we are compiling them using the EM script, and then compile our player using those libraries, and then JavaScript imports that WASM file and uses that in sync, and JavaScript feeds byte buffers into the WASM and receives pixel buffers, and draw pixel buffer on the WebGL. How does it look like? This is the overall some sort of sample code in there. We are using the EM script in version 2.0.8. Please consider that this version of the EM script is a little bit older. There's new version, like I guess the most recent version is 2.0.15, something like that. So things may be changed, and they are actually for a fact. You see that we are using the EM configure, and there are multiple tutorials on the internet on how to compile and generate WebAssembly version of the FFmpeg. It's a bit different here because we don't need most of the features of the FFmpeg, like the CLI, like the many muxers and demuxers and the codecs. And you see that our goal was to generate the smallest possible binary, the size based on the features that we need, like H.264 and AAC decoder, parser, and MOV move demuxer, which is needed for the MP4, and using the EM make to make it. And then we are compiling the player, again EMCC, with the EM script and version 2.0.8. There has been difference. There's a difference between the newest version of the EM script and this one. For example, I guess in the newest version you don't have to expose the actual function names. I'm not sure of that. And you can see that we are using the LAV format, LAV codec, and LAV util. Those are the libraries that we compiled in the previous step. And you can see that the EM script generates the glue code for you in form of index.js. And the components, these are the components. There is a main thread that runs the game. By game, I mean that what I mean is the JavaScript front end of our game, which sits on top of the video player and provides a way for the players to interact with our games. And there is WebSocket worker, which sits in another thread. Basically, we could replace that WebSocket part with anything, any other transport protocol as we want. And there is this another thread runs the decoder worker. And the reason for this separation is that when the game is heavy, which is in many cases, that could hurt the video playback. And the results so far, and our goal was to achieve sub-second latency, and we achieved it. These are the screenshots of the tests that we've done a while back. There has been some changes and updates there, so we are hoping to achieve even better latency, lower latency than this. On the left side, you can see the WASM player latency of 0.9 second versus our current production player, which is offering 1.8 second. This is a picture of a clock, a laptop with the time on it synced with the NTP server, and the time on the local machine on another building, and the times are synced together, and you can see that the latency is sub-second already. It has the seamless adaptive bitrate switching feature in it, and it is currently playing back on the iOS, Androids, and desktops. And what are our future plans? Improving performance, of course, using shared array buffer, for example. It is right now not supported on Safari, hopefully in future. We are hoping WebAssembly, CMD, offer screen, canvas, audio worklet. The goal is to improve the performance, and if we are getting a better performance, that could lead to better and lower battery usage. As said, we are right now achieving between 80 to 90%, depending on the various situations of the native playback time of the HLS playback. And reducing player bundle size also is another goal. Right now it is around 500 kilobytes, and we are thinking that we could reduce it to like 150 kilobytes less than what it is right now. And hopefully in future, when web codecs are becoming available and supported in all browsers, we don't have to deliver the codec anymore, then it will be even smaller file. Thank you for your time. I try to be really brief and fast so as to not take up the time of the other wonderful speakers. Please grab me either on Video Dev Slack channel or over the live chat on Twitch. I'll be happy to discuss and answer your questions. Thank you very much for your time.
Hi, today we will talk about digital rights management, or DRM, in video, and whether the video is played back from a mobile device or a desktop or a smart TV. There are steps and technologies behind that allow for premium content to be played back safely and decrypted. So video is actually encrypted, and there is a whole process behind to make sure that the person that is consuming and plays back the video is authorized to do so. So I've created a graph here of the different steps in a DRM system, and the first one is actually the users. So the users log in via authentication to get access to a catalog. That's the first step. Once they've logged in and they are browsing the catalog, they can make a video selection. So they choose a video, which means that a request is created for a content type to be played back. Then that video selection request, so probably has a content ID, is conjunction added to the requesting device ID, which basically is a sort of a signature. So more than an identification, it's a long, you don't think of it as a string, think of it as a sequence of bytes that are unique to the requesting device. So we have two pieces for now: the content ID that the user has chosen, plus the signature of the requesting device. Then the next step is that the video is fetched from storage, so like a CDN, and the video we divide up here into segments that represent the different quality levels that the video can play back at, depending on the user connection and requesting device. So for example, if it's a mobile device, it will have a lower quality because you don't need 4K on a small screen. Whereas, for example, with a tablet, you're gonna have a bigger kind of screen size, so your quality will increase also in function of your internet speed. So once the video is fetched from storage, the license of it is checked via the browser component that kind of reads the type of DRM system. There are multiple types, which was used to encrypt this video, and you can encrypt either the segments or the metadata. So once the DRM browser receives the DRM component in the browser receives the request for the license check to play back a specific video, what it then does is contacts the DRM license server, and it says, okay, is this user, which was out here and that has selected a specific video on that device, is it allowed to actually play back that video? So this information gets aggregated together in the DRM license proxy server, which checks the user credentials. It also has a license database, which includes information like the content ID, so the video selection here, device ID, which we can kind of associate to the requesting device, so the client signature. It has a key ID, which was brought out from the manifest of the video, or what describes all these segments and how they are related together. And it can include policies and also permissions. So all this information is stored in a license DB, which then the proxy server contacts to actually get that information for the license. So we then check if the users on that device can view the video, and this is the job of the proxy server and the license database, usually set up by the service provider, which is different from the content provider. And once the DRM license proxy server has made a decision whether the user is allowed to watch on device that he's requesting to, it then serves back the license to the DRM browser component, which then uses the key from that license to decrypt part of the video and actually play it back. So there are a couple of steps. Let's go through them again. The first step is that the user logs in, they're authored, they select a video on a specific device, then the video is fetched from storage, so from the CDN, which is a server close to the users where the video is saved. It is then sent to the browser. The browser DRM component then asks for a license check. The DRM license proxy server verifies that the user is authorized. It also checks with a license DB, which contains different information like the key ID and the content ID, and all of these together tell whether the user is allowed to watch a specific piece of content on a device. If the user has that permission, then the license server sends back to the DRM browser component the key to decrypt the content and play back. So hopefully that was kind of a general introduction. Thank you.
Good afternoon. My name is Luca, and I'm very happy to be here as part of this 24 hours video tech meetup that is really global. It's really amazing. And today I'm going to show you some tests that I did around this new KPI format that is called CMCD, Common Media Client Data, and a new way to push raw logs data from Akamai to an external log aggregator. In this case, I used Datadog. Let me share my screen because I really want to start by showing you what I did in Datadog. This is really a kind of video KPI dashboard that is not using the client data of tools like Nice People at Work or Max or Conviva, but this is a nice way to complement all these client-side tools, and actually is using the logs that the edge, the CDN, in this case Akamai, is collecting. All these logs are being pushed to an external log aggregator. In this case, I'm using Datadog, as you can see, is in less than a couple of minutes. So this is really a nice way to get additional visibility to what's happening on your user's device. So let's start saying that for this test, I used a simple player. This is dash.js. I built this very simple page, and you can notice that here on the right, the player for any request that is doing to the CDN is adding additional data in query string. So you see that this has been parsed, but if you open any request and you open also Chrome Tools, you see that on top of the request URL, there is a query string, some query string parameters that are tagged with CMCD equals to buffer length, for example. This is bitrate. This is D is the chunk length, and so on. We will see some of them in my dashboard. And this is really the flow. So the clients with dash.js are performing request to the CDN. On top of each single request, there is some query string parameters that are tagged with CMCD. That actually is this new way of adding additional visibility from the player to the CDN. Akamai, of course, is serving the content, but is also aggregating. Let's say that it's also collecting all these logs and pushing them raw, really not doing any kind of aggregation, to this collector Datadog. So on Akamai, we're using datastream2, the version 2, to push these logs, and the logs are being pushed in less than 2 minutes. So usually it takes 60, 90 seconds to push the raw logs. So you see that here we are gaining additional visibility on what's happening on the clients because we have this additional metadata. But let's see a little bit more in detail this dashboard. First of all, we can count the unique session. You see here that it's 6. We are able to count them because basically in the CMCD there is a parameter that is called SID or SID in Italian, let's say, that is the unique session ID. So for each play, and actually you see that we had 3 from Italy, 2 from Germany, 1 from France, we're able to tag each single play with a unique session ID. And you see also this ID, for example, here, that is a CMCD.SID, and then there is the unique ID, for example. You see that we had some plays from Turin, that is actually where I live, from Munich, and go on. And we are able also to show all the 200 status code per country, and also we are able to draw nice dashboard because, for example, you see that in blue most of the requests were 200 on 206 because I'm using also byte range, but actually we had some 403 that are actually basically happened 1 hour ago. You see here status code 403, and most of them are from Italy, for example, from Turin, that I simulated some 403. And you see, for example, here that you can also have the logs, so error logs, for example. You see that if I'm opening, let me search a request from Italy, for example, this one. I'm opening this request, I will get the access really to the raw log. So in this case, you see that the request host was correct, but I used a request path that simulating a results that was not present. And in this case, I got the 403. And then you see that I have also some additional data, but we will see them later on. So on top of this error, we are also able to count the rebuffering that are happening. For example, in this case, 1.6% of the total requests were tagged with a tag that is called BS. It's actually buffer starvation. And it indicates that that request was in a buffer starvation mode. So basically the payer stopped playing the video, requested the content. Actually, we had 12 from Germany, 6 from Italy, you see clearly here. And you can, of course, also access the raw logs. For example, here in the rebuffer logs, we have, for example, from Italy. Let's click on it. We have in these query string parameters, BS, you see clearly listed here that if this tag is present, is equal to true, this indicates that the request was in a buffer starvation mode. And then you see that basically here I'm parsing with Datadog some of these requests. For example, I'm using this node CMCD -CSV, and I'm extracting with test3. I use test3, of course, in a production grade environment. You may use a better naming convention, the tag BS. So in this case, we can really see that these, I don't know how many, but it should be 18 requests were tagged with this BS KPI. But let's go on, because of course we can see also the distribution of these buffer starvation requests, and you see that here, for example, we had 6 basically 1 hour ago, but we can also extract some additional data. Let me zoom in a little bit because here the text is a little bit little. So we can see here, for example, the edge throughput per country and per session. So in CMCD, we are really able to count each single session ID, or we are able to group them by country, and we are able to list the to show the throughput that actually the edge had with the client, with the player. And we see here that basically in blue there is France with this spike. So basically it was just a play that it happened as a couple of minutes. But then we have also Germany, for example, that is in violet, and Germany basically 1 hour ago had a 10 minutes play that was actually almost 60 megabit per second. You see that. In yellow we have Italy, and you see here that in Italy I was able to play the video at 40 megabits per second. But then we have also the unique session ID, and in this case you see that this average was 1 megabit, this average was 3 megabits, this was 30 megabits, this was basically 1 megabits because I applied some bandwidth throttling on my Chrome PC. When you see that this KPI is called MTP. So when you see MTP, this indicates the edge throughput between really the edge and the client. Let's go on, because here we have also the played bitrate per country. You can do that also per single session ID. In this case, you see that Germany, that is violet, had quite a nice played bitrate. The top was 4.2 megabits, as well as Italy, for example. You see that in yellow, this was 4.2 megabits because this was the top bitrate of my Big Bang Bunny video. And then going on, we can have also the buffer lengths per unique session, for example. And you see that, or you can aggregate the data also per country, per city, per continent, of course. And you see that basically the yellow session was able to have a maximum here of 30 seconds because in dash.js, when you play the top bitrate, you will get, of course, for a VOD, a buffer of 30 seconds. In this case, for example, this was just a buffer of 5 seconds. So this indicates that maybe it was not playing the top bitrate. Usually dash.js is setting up the buffer to 12 seconds in case it's not able to play the top bitrate. You see, for example, here for this playback that is 11.7, 11.6, 11.68. So in this case, we were not playing the top bitrate, we were playing maybe this was the 3 megabits, you see 3 megabits bitrate. This was per country, but anyway, basically I did display. I was alone in Italy doing display for this video, and then we had the buffer length that is set up to 12 seconds. And then I can have also some additional data. For example, I'm doing the log count per request path, and you see that the top bitrate for the 2 megabits is clearly the one that is having most of the requests. I can see if the status of the cache. So most of the requests, for example, are in cache. There is just some here that are not in cache, that are tagged with 0, while one is in cache. And then I can really list all the devices. For example, I had 3 playback from Chrome, 1 from Safari, but if I expand the time frame, I had also actually 1 from Firefox. And then, of course, I can list really all the logs that I'm having. For example, this is a request that made from Italy. You see again that I have some data. I have the request path, I have the host, the port, the request time. I had the content type, the TLS version, the status code, so the user agent. I have a lot of data. I have, of course, the IP, and on top of this, I'm using some parser in Datadog, for example, to parse the IP and to get the geo. So, for example, this is me in Turing, or to parse the request path here, the query string here, and to transform all this data in this variable. So, for example, this is the BL buffer length, 30 seconds. This is the BR bitrate 4.2 megabits per second. This is the chunk length. This is the throughput, 65 megabits per second, and so on. So I think that this is really helpful, I guess, to have this additional visibility. And you can simply search on Google CMCD, Common Media Client Data, to get additional explanation. There is some very useful link, OTTverse, Front Offer, GitHub, OTT Ball. This is also the mile height video. This should be, yes, these are the slides from Willow, and I think that the video is also present on YouTube, but it is explaining really what is this common media client data, and I think that also that we will have a session later on in this global 24-hour meetup. And you can even search Akamai data stream 2, for example. You see here that you get the user guide, you get the page developer.com with API, you get the marketing page, and basically you see here that there is the user guide. It's very, very simple to set up. We are compatible with Amazon S3, Azure Storage, Datadog, Google Cloud Storage, and Splunk. And of course, this product will evolve in the future, so we will have more compatibility with additional destinations. So I really hope that you enjoyed this session. It's really a pleasure to be here as part of this global video meetup, and enjoy the next session. Thank you.
Hello, everyone, and thank you very much for this opportunity to exchange ideas and experience with the colleagues from the video industry. My name is Alexey. I'm working for Elecard company, and Elecard is a software developer for the digital video solutions. We work with live video encoding, streaming, and quality solutions, quality control solutions. We engage also in the head-end deployment for OTT IPTV and DVB providers, and in quality assurance for the distributed video delivery networks. And today I will focus exactly on this topic, on the video quality assurance in distributed networks in video delivery. So let me share my screen. I have a few slides for you. Okay, should be coming up in a minute. Okay, I will start the presentation. So my presentation is about tips to improve quality of OTT and IPTV content delivery. And for that kind of projects, we in Elecard utilize distributed monitoring solutions. Usually distributed monitoring consists of several parts. There is a central server and client applications or hardware probes that can be distributed over the network at different stages of content delivery. So why is it important to have that kind of monitoring solutions in the network? So because in such projects, in OTT delivery and IPTV networks, usually several partners are involved, including content providers, those that prepare the content for the distributions, and also the main content distributor, and then the regional providers. Sometimes it involves satellite uplink and downlink and so on. And so the content is being converted or changed in some way, and you always want to know what kind of quality you receive on the output of each stage of content preparation and content delivery. So that's why the distributed monitoring solutions are important. And today I will share some real-world use cases with you, with real-world clients from OTT and IPTV landscape we faced during our support activities for such projects. And the first case happened with our client when the end users, the subscribers, faced stuttering on their devices. So there were some TV freezes and blinking during the ad breaks in regions. So we installed 2 probes. In this case, the first probe was installed before the transcoder and splicer, and then also before the DVB modulator in the region. And we detected no problems on the transport level from headend to region. So the stream was okay, the bitrate was good, and there was no packet drops, no continuity counter errors. But the probe in the region detected the video elementary stream problem, the so-called video information changed event. That's an important metric, which signifies that some part of the video has different parameters from the main workflow, from the main program, and how it can be seen in a monitoring solution. So there are usually logs and graphs in which you can see those metrics in any monitoring solution available. We use our own monitoring solution, and so there is a reported issue with video information changed in the logs. And in this particular case, the video of the inserted ad had different aspect ratio from the main program. It had 16:9 aspect ratio instead of 4:3. And some end user devices just cannot adapt on the fly to the changing parameters on the video, and they just stop decoding and they wait for the parameters to return to their original values. So it really gravely affects the quality of experience of the end users. And so the solution was to ask the original provider of advertising to change the video parameters of their ads to be inserted. Right, so that's how this quality issue was solved. Okay, going on further to the case number 2, when the streams became totally unavailable for the end users. And this time, the content distribution network included the satellite distribution, and we also installed several probes here after the satellite demodulator, and then after the transcoding module. And it turned out to be that on the output of the demodulator, there were some problems with the scrambling module, and the stream sometimes became turned again to the scrambled mode. So how it can be seen in the monitoring solution. So here we can see the special flag in the logs, signifying that, okay, there is scramble and it's true, and there is scramble and it's false, meaning that the stream is being descrambled, but then turning again to the scramble mode. And we also couldn't analyze the audio on those periods which were scrambled. And the solution was, of course, to replace the faulty scrambling module in this case. All right, going forward to case number 3. This time it happened with the OTT client, with the OTT platform, when the players of the end users just stopped working, stopped decoding and playing back to the OTT streams. So it was a big provider having CDN service across whole country in different regions, and we installed more probes in this case. Some of them were installed on the head-end station before the transcoder packetizer and after it, then after the origin of the CDN, origin output, and then also in the region on the CDN input and on the CDN edge output. And there were no problems detected on the head-end station, but in some regions, in some CDN edges, we detected that some segments of the HLS broadcasting were just absent, and the load speed was too low for the real-time playback. That's what prevented the OTT players to play back the streams. And how it can be seen, which metrics you can use to identify that. So usually the graphics for adaptive bitrate download, it looks like this, like peaks when this segment is being downloaded. And there were periods when no segments had been downloaded, so they were just skipped, and the decoder had now enough data to play back the streams smoothly. So the solution was to extend the bandwidth between the CDN origin and the CDN edges in regions. So the service came back to its proper broadcasting. Okay, going forward to case number 4 now. This time it also involved some part of the network being satellite transmission, and in this case some TV channels became unavailable or highly distorted. There were some pixelization or absence of pictures at all. And in this case we installed the probes also at the head end, before transcoder, before satellite modulator, and then in regions after satellite demodulator. And we detected some issues in regions. So in the streams, there were a lot of errors on the transport level. So a lot of data was just missing, a lot of packets was lost on the way, and a lot of continuity counter errors repeatedly have been shown in the monitoring solution. I can show you it here. So we used 2 main metrics here, and continuity counter errors. Here you can see them as a purple lines. Also medial loss rate and the interpacket arrival time. Interpacket arrival time is also a very important characteristic, and it shouldn't exceed 50 milliseconds. So it's the time between the packets arriving to the probe, to the encoding device, and to allow proper and smooth decoding. And also it happened during the same time in the day. It was happening during the evening hours. And later on, after some investigation, we detected that there was an interference between satellites at evening time. And so we had the operator had to change modulation parameters, and so the proper broadcasting was restored. All right. Then going further to case number 5, when the users experience the absence of sound at the end client devices. So here also we just installed the probes at the transcoder input and output, and on the subscriber side after the DVB demodulator. In this case, we detected no issues on the subscriber side, but the probe installed on the transcoder input notified us about the PID lost event for one of the audio channels, and meant that, so here you can see it on the graph, that the certain audio PID was missing and there is no payload for it, and so we couldn't analyze the loudness of audio on those segments of stream. So the issue was reported to the content provider because it was on the input to the transcoder, and it was quickly fixed then with exchanging the the stream and fixing it up. All right, and the last case I wanted to share with you today is also concerning the OTT streaming, when one of the subscribers for OTT service experienced some video freezes and stuttering also on the end client side. In this case, we used 3 locations for analysis: before the transcoder packetizer, after, and after the CDN on the CDN output. And in this case, there were a lot of problems on the transcoder output actually. So there was a significant number of packet losses on a transport level. Oh, I'm sorry, it was detected on the transcoder input rather. All right, and then the transcoder receiving that hidden stream on the input just turned to the static picture mode. And even when the stream was restored, the transcoder couldn't return back to the live encoding mode and still translated the static picture. And so in this case, the only solution was to exchange the transcoding equipment. So it was replaced. All right, that's all I wanted to tell you about the cases. We faced some common cases for the OTT IPTV providers. I hope it was useful for you, and maybe you faced such issues in your work. Thank you very much for your attention, and enjoy the rest of the meetup. Thank you very much.
Thank you. Hopefully you enjoyed today's event and the 24 hours mega meetup. And if you haven't already, sign up to the meetup group, and see you soon. Thank you.